Merhaba. Hi, this is Ahmet Ergenç from Circle. I think we are having our participants now, the listeners. Now I'm here to make a short presentation, and then I will leave the scene to Yuksel and Mine Hoca, and you will be able to participate in that presentation. This is our second seminar related to R&D studies of Antarctica Studies Center of ITÜ. Today, there will be three groups making their presentations. Presentations will last about an hour, and if you have any questions, if you have any comments, you can type your questions in the question and answer section you will see on Zoom. And these questions will be answered by the presenters after the presentation. Now, I think I made a mistake. There are four groups. And if you have specific questions, please try to mention the name of the group before your question. So that group, the participants of that group will try to answer your question. Yes, now I think we have most of our participants here. So we can start first. Yuksel Hoca and Mine Hoca will start with an introduction. So Yuksel Hoca, I'm leaving the word to you, and welcome to all of the participants.
Thank you, Ahmet. Thank you, The Circle, for having us here and helping us share this word with the world, actually. And also, weird to say, but thanks to the pandemic, so we have these platforms now functioning effectively, so we can communicate, through this digital platforms and spread the word. So as you remember, in the first webinar, I shared the experience of our research group regarding the design studies of Turkish Antarctic Research Station. And as you'll guess from the headline of the webinar, the role of R&D in architecture is our main, actually, let's say, mission or concern here, or concentration here. And I was also mentioning also that we are working in our both undergrad and graduate programs, trying to integrate research and development with architecture using systematic, scientific and objective approaches, design approaches. And today, you'll be seeing the outcome of the studies that we did with Digital Architectural Design Studio students. We have 4 groups. And that's a master program in Istanbul Technical University under the title of Architectural Design Computing. And we did this course co-supervising with Professor Ozkar Kabakçıoğlu. She's also here. And 4 of our younger friends, Burak Delikanlı, İnanç Şencan, Müge Halıcı, and Koray Bingöl, thanks to for their contribution as well. And our friends in these 4 groups will introduce themselves and their friends. And I'd like to pass the word to Mine to say a few words about what we do, how we do in this program. Thank you very much.
Yuksel, thank you. Hello, everyone. We truly appreciate the interest. I see the number of the participants rising. I want to briefly give context to the group of researchers presenting tonight and the work that's going to be presented tonight. Yuksel and I, along with the 4 young researchers that he mentioned, Burak, İnanç, Koray, and Müge, we work at Istanbul Technical University, Faculty of Architecture. And we're also part of this wonderful program. It's a graduate level program, but it's actually an active research group, a big research group called Architectural Design Computing. And every year in the master's degree program, we have a digital architectural design studio course. It's a required credit. And it's a great opportunity for also not only the students of the program being able to come together and collaborate on something. It also allows the program's knowledge to be put to use, actually. So the design studio that we also co-taught this year focuses on research. It's oriented towards a research understanding of design, much in tune with the program's approach, actually. The program is not new. It's been around for over 25 years. And it's been a vanguard in Turkey in this field. And it focuses on design inquiry, design research, and how that relates to design technologies. And through the works that are conducted in the design studio, the digital architectural design studio, some ideas are put to use, some methods are put to practice, applied, sometimes methodology is developed. And approach this year in the digital architectural design studio centered around the methodology of systematically identifying decision criteria for a complex and data-driven architectural design problem, such as the National Research Station in an extreme environment, Antarctica. So this is the link to the research and design oriented architecture Yuksel talked about last time. And the works that we're going to see today reflect the outcomes of the studio this past semester. It just finished actually a couple of days ago. The semester ended on just this week of this academic year. And in this semester, when we tackled the problem, the general problem of designing or how to approach a design problem for a research station in Antarctica, the group of students and we came up with ways to diversify the problems, identify sub-problems, and settled in 4 separate sub-problem groups. And we will have outcomes of the research that those 4 groups have tackled. One of the problems that the design demands from us is the issue of how to settle and where to settle. So the first group that we're going to hear tonight is going to be focusing on that. And the computational issues around handling that vast data that feeds into solving that problem. The second sub-problem that was identified in the studio was the design typology for the station building, the actual building. What could be the typology, organization of its modules, etc. And that was tackled by the second group, who focused on a modular design of a settlement and how that module can be in fact devised and built. Another sub-problem identified was the well-being of the individuals who inhabit in the station and the researchers. And the third group dealt with that with very much interdisciplinary care and devised a winter garden. And the last group dealt with the last sub-problem that we were able to identify in the studio, which was the interior space organization. Together, these four sub-problems do not perhaps form a unified picture for a seamless unified picture for research station design in the Antarctica, but they do together work at least to present us a partial picture of what an overall design might be. Not as an outcome, but as what kind of criteria are involved in designing this mega project. So without further ado, I would like to pass the microphone to the first group, who, as I said before, is focusing on this idea of the settlement and the technical problems that identifying a placement for the station presents. And for that group, Barış Doğaçam is with us on the panel today, and he's going to present on behalf of his group, and he'll give you more information on who the group is consisting of too. Barış?
Hi, hello. Let me just share my screen. Okay. We were a group of five. We are named Group 4. We were Dilara Temel, Sevgi Altun, Nurdan Akman, Kartal Turan, and I, Barış Doğaçam. And yes, we're the settlement group. What we basically did was, throughout the semester, we designed an algorithm that takes the topography data as the main parameter and then generates different possible settlement alternatives. And then we test all these alternatives through simulating the environmental conditions of Antarctica. And then finally, we evaluate and rank them, and we get the best result. So this is our schedule throughout the semester. And well, about the matrices, as our professors have just mentioned, we embraced a systematic approach in the studio. And well, we try to avoid the architect's intuition, or we rather try to demystify it. And instead of taking seemingly arbitrary and intuitive design decisions, we wanted to be able to justify all the decisions we made. Therefore, we used a lot of matrices, which you will be seeing a lot throughout this presentation of 1 hour. And here you can see our decision matrix, where all of the design decisions and their possible outcomes were discussed, and all of them have influenced the algorithm at the end. And the decision matrices in turn resulted in the morphological matrices, which enabled us to be able to change every parameter and see their immediate outcomes in the results. As I told you, we were designing how we can settle in Antarctica. So we started by deciding on what kind of a settlement it was going to be, and we decided on a modular settlement, and we classified its functional units into 4, and that way we were more able to tackle with the problems. So we have 4 functional units, which are the service areas, the research areas, the common areas, and the private sleeping areas. And all of them have different requirements respectively. And this affects how they are joined together and how they're placed and how they relate to each other, their relationship with the slope, topography, or the accessibility issues. Uh, just to give a small example, a service module has to be accessed vertically and horizontally, whereas a sleeping module is not necessarily needed to be accessed. So we dealt with these kind of issues. And on the bottom left, you can see a very, very simplified version of our final evaluation, which I will be talking at the end of the slides. Now, what we did was, instead of designing for a generic Antarctic or Arctic place, we wanted to, since the settlement issue has a strong relationship with the place and the location, we wanted to design it for the very location that the actual Turkish research base is going to be built, which is the Horseshoe Island. And it is one of the islands on the western coast of the Antarctic Peninsula. It's close to South America, you can see. And we created a 3D model of the island using the satellite images, and we retrieved the height data from these images. Now, as you can see, although it is an island and one can assume that you can approach an island from all sides, as you can see on the photos on the right side, throughout the year, most of the surrounding of the island is covered with ice, and only in the Antarctic summer is when you can approach the island from all sides. And apart from that, if you want to approach it throughout the year without any problems, you would have to use the big bay on the western side. You can see it with the red dot here. That is our main point of access. So that was a big issue on deciding where to settle and how to settle. After creating our model of the island, we analyzed it in terms of the slope, elevation, and how different points have different views of the island. We used many simulations and precedent research. We used our wind analysis to see where there are really high winds, where we cannot settle actually. We also used the slope of the island and the possible fauna and flora. And on the top left corner, you can see a map. It is a geological map created by the researchers of our university. So we used all of these to see where we can settle in the island, which is the most suitable place to settle. In the studio, as our professors have mentioned, we used a lot of previous research, and we used also previous precedent analysis of the existing already built, constructed research bases in Antarctica. And they were classified into 4 types. First, we have the singular type. Second, we have the linear type. And we have the radial type, like the Jangbogo, and we have the fragmented type, which is more like a village or a town than a small research base. We did this analysis in order to decide on what kind of base we wanted to design, and it was going to affect our way of settling on the island. And then we further analyzed the possibilities of these different settlement types. Here you can see the examples of these types already built in Antarctica by different nations. In terms of slope, we found out that the radial type was not at all suitable since it is designed for a plane surface. The fragmented type 4 was quite outdated, and it is financially and naturally not feasible, we can say. And we found out that the typology that was most promising and exciting for us was the type 2, the linear type. And from there on, we started to design our base and its algorithm. We also dealt with how it is going to relate to the slope and its angle in terms of section length, and how its leg height is going to change. We also used previous researchers' information in terms of how different bases use their space for their population. And since we decided on a linear and modular base, we used a previous design of a student from our university, which was from one of the classes done within the framework of this research project. We chose it because of its modularity, and also many of the features of this project were in accordance with our decisions that can be seen in our decision matrix, like the fact that it is raised from the ground, or it's easily transportable, adjustable to the slope, and that it can be easily put together and separated, and it is really suitable for a modular settlement. What we did was basically, this is a flow chart for our algorithm explaining how it works. After creating the model of the island, we divide the island into a grid whose cells have the exact same area as the modules of our base. And then we determine all the barriers, well, the places we can and cannot settle. And then we start placing our modules on the places we can settle. And one module after another, we settle, the algorithm settles, doing a calculation of the elevation and slope around the cells of it. And the algorithm constantly checks if it has enough amount of cells for the population. And at the end, when it has reached its final design, final layout, like here, we subject the outcome to several tests. These tests, some of them simulate the environmental conditions, some of them are related to its accessibility or its location, and all of these tests have different coefficients in the final evaluation, which I'll be talking later on. Now, in order to showcase the possibilities of the algorithm that we designed, we wanted to give you 3 examples. We overlapped all of the barriers of the island. This is a map of superposed map of all the barriers of the island. So the red places are unsuitable for settling and the white spaces are okay to settle. We decided on the valley in between the 2 mountain ranges. You can see the 3 areas we chose. And we analyzed these 3 areas in terms of its distance from the shore, its accessibility, its maximum wind pressure, its view shed, etc. Wind is especially really important in Antarctica because it can be really, really strong. And in these analyses, we used the maximum wind speed ever tested in Antarctica, which is 85 meters per second, more or less like 300, 350 kilometers per hour, if I'm not mistaken. So how does the algorithm actually work? The algorithm places a module in a cell of the grid and then goes on checking every cell around the grid to see if it is suitable for settling. What it does is it calculates the distance between the level of the settlement and the ground level. And if it's okay, if it is within the limits, it places another model there and so on. And it goes on until it gets the sufficient amount of modules to provide for its population. In order to be able to demonstrate the different possibilities of this algorithm, what we did was, since we use a grid and a grid can be quite limiting, we rotated the grid. In the first row, you see settlements made with a grid from that goes through north to south, from east to west. And in the second row, you see the same grid rotated 30 degrees, and on the third row rotated 60 degrees, so that we wouldn't be limited by a Cartesian grid. And here are the outcomes. Now, these are small GIFs of how each and every settlement was generated. Now, the algorithm first puts the 3 modules, which are the service modules, and then places the other 3 modules, which are the research modules. And afterwards, it places the FAT module you see, that's the common module, the common areas of all the researchers who live in the research base, and then the sleeping areas. And afterwards, after placing all of them, as I mentioned, we subject the outcome to several tests and simulations. You see the wind, the sun exposure. The third row, this one is quite interesting. It analyzes the maximum walking distance within that generated plan and the location of its service module. If it's in the central, if it's in one edge, and all of these have different values, it gives them different points at the end, at the final evaluation. And finally, we analyze their maximum leg height. So if they're in a steep terrain, it's not a really good alternative. If it's in a more plain terrain, it's a good alternative. So these are the other ones. So as you can see, it's the same topography. What changes is the angle of the grid so that we wouldn't be missing out on different possibilities by the fact that we were using a grid. So we just rotated the grid. And the same analysis for these three. And finally, the last three examples. Sometimes the algorithm can generate a quite linear and longitudinal snake-like layout. And sometimes it can generate courtyards or quite compact bases. It's really up to the algorithm and the values we gave the algorithm, of course. And at the end, the final evaluation, we retrieve all the simulation data and all the analysis data, and we remap them. We give them a value between 1 and 0, and all of them have a point, have a score, and then we multiply them by their coefficients. As you can see, for instance, the wind analysis has a weight of 4, whereas the wave shed analysis has a weight of 3, which is less important than wind. Sun exposure is 2, it's less important. And shadow analysis is 1, as you can see. And at the end, we get a final evaluation and a ranking, and we get a best result and a worst result. So this is our best result from the 9 different possibilities that the algorithm generated. And for future research, as you can see, we dealt with right angles in our algorithm. One can further develop our design and try to do another design working with hinges, giving the possibility of different angles. Another future area of research would be the mobility of a research-based design like this, because ours was static and stable. Another further research can be the form of the module. Since we used the pre-designed module, we didn't deal with its shape, but you can design it in terms of aerodynamics or more sunlight, etc. And finally, what we tried to do was to take the qualitative side of architecture and to engineer it and give it a quantitative way. I hope we managed to do it. Thank you for listening.
Thank you, Barış, so much. This was, I think, a very clear account of your group's research. As we move on to the second group that focuses on the module design, we will see that groups tackle different aspects of the larger design problem. But they also communicated and worked as part of the larger group. Not only the knowledge that accumulated in the studio, but also the knowledge that keeps accumulating in the entire community of interest was utilized. So there are overlapping elements between the groups and previous work and research that's been done. So without further ado, I'm passing now the microphone to Ekin Kılıç, who's going to be presenting the work that the second group did on behalf of his group.
Hello everyone, and thanks for making this happen. We are OptiModule group, and we focused on creating a module. My name is Ekin Kılıç, and my friends are Betül Şen, Atra Haddur, Deniz Tutucu, Elif Gamze Dedeler, and Tahsin Ozkar. So we wanted to create a module that can adapt to any settlement plan and any floor plan. And we wanted that to perform a very good aerodynamic performance. And we wanted it to have the least heat loss. So we wanted to optimize it by using computational design methods and simulations. So we had some goals and some criteria, and we use project management and project charter tables, as you can see here, to distribute the tasks among group members and to set some goals. You can see they are all completed. And we used project matrices to, as you can see, there are multiple solutions for one goal. And we wanted to select the best solution for us. So we gave them numeric numbers, and the highest number is our choice, the one that fits us the best. You can see other matrices here. And so we wanted this settlement to be modular. We wanted it to expand over time. So the first pioneer base is settled. After some time, it is going to expand. And we wanted to have a grid because of this goal. And we looked for some plan geometries, as you can see here. And we had some criteria like the rigidity against stress and a gap between the modules, if there's a gap or not, and material usage, and hexagon performed better than other geometry. And we also did some wind tunnel tests to see if our geometry performs good under wind loads. And as you can see, hexagon didn't perform well under when it is only one module, but when it creates a settlement, it's not very different than other geometries, but we had to optimize it aerodynamically. And after selecting our plan geometry, we looked at the projects that were done before us, and we chose this project, Beyza Sertoğlu's project, because it fits our geometry, and we decided to develop it further. And at first, we looked at the existing Antarctica stations to give us some base numbers like ground clearance or floor height or panel thicknesses. And after getting these numbers, we started to design. You can see a basic flow chart of what we did. We decided it to be modular, the settlement, and we decided on the form. Then we started optimizing it, performed some wind tunnel simulations, did some structural analysis using Karamba 3D plugin for Grasshopper, and we also optimized facade openings. And you can see what we did to the geometry here. We pivoted the corners and chamfered some edges, and we lifted the module from the ground. And we also decided on the foot geometry and how high the foots are going to be, how high the feet are going to be. And we also optimized panel openings to find the ideal sizes. You can see some of the parameters we can change. So it is designed in Grasshopper. And what Grasshopper does is it creates some hexagonal profiles and then creates surfaces between them. And that's what creates this geometry. You can see the code here. And within this code, you can change some parameters. You can see which parameter affects which part of this geometry here and how it looks like in an existing Antarctica station, which is LA4 here. And we can create various alternatives by changing these parameters within a short period of time. But of course, there is only one optimal solution. And to find this solution, we used an evolutionary algorithm called Wallace, which is also in Grasshopper. And we told this algorithm to change the parameters I just showed you to create minimum surface area to volume ratio to minimize heat loss. And we ran this algorithm 3 times and it gave the same results every time. So we decided that this is our optimum geometry. You can see the final parameters here. And after deciding this geometry, we looked at the existing feet that are used in Antarctica stations to give us a base. And we looked at which one performs better for our geometry. And green one performed better we used Karamba for this analysis. And after deciding the feed, we also did some wind simulation tests again, you can see at the bottom right, to see how much ground clearance we need for the wind to blow under. It shouldn't be too low because it would prevent the wind and that would pile up some snow around the module. We don't want that. And it shouldn't also be too high because that would restrict accessibility and maintenance. So we, after our tests, we concluded that 2 meters was enough for us. You can see how Karamba works here. And after the geometry and the feet are decided, we started to panelize this module. You can see there are 6 different panel types, and by rotating these panels, you can create the whole module. And for panels 2 and 4, we created some openings. You can see the various panel alternatives at the bottom right. So after creating some types, all these panel types have different parameters. You can see some of them on the left. And by changing these parameters, you can also create different variations of the same panel type, as you can see at the middle. These are all an opening type we call linear hexagons. You can do this with other panel types. And after creating these openings, we had to optimize them in size. So all these panels have an opening ratio, but there is just one optimum ratio for, let's say, every volume. And after creating the floor plans, the user can come and calculate the ratio here and give that ratio to the code. The code will use Galapagos algorithm to match the 2 numbers for the panel, and it will change the variables and keep the constants to match these numbers, to equalize these numbers. And as you know, Antarctica has strong winds and powerful storms can happen anytime. So we had to protect the openings with some external force protectors. We designed some force protectors, as you can see here, for each opening type. And also the Antarctica has a day-night cycle that is very extreme. So we had to add some light controllers to match the daylight that is allowed inside with our circadian rhythms. So we designed some light controllers. And you can see here how they all add up together. And about then we start to look for the materials we are going to use. You can see all the materials as a list that are currently used in Antarctica stations. We used the materials that are you see here. And also we looked for some stations like Halley 4 and Princess Elizabeth, which materials they used, what kind of details they have. And we created our detail, our layering. You can see it on the right here. And we also decided on the material of the opening, which is fiberglass window. You can see the layering here, how all these materials come together to form a panel. And after all this, we started to make some fire simulations in case of a fire. And basically, we looked for the materials, we looked for how many surfaces we need between the modules, and we also looked for if we need distance between the modules. So double surface performed better, which means on the left here, each module has its own panel, and glass fiber reinforced polymer performed better than steel, which is our material. And we also advise 3-meter distance between the modules to prevent fire from spreading faster. And you can see the tests done with single and double surfaces. And you can see the tests both with double surfaces, but different materials like steel and glass fiber reinforced polymer. And this is a test done with a 3-meter gap between the modules and no gap between the modules. You can see how fast fire spreads. And this is a video, but I'm not gonna show you because of the time. And we also have we created a detailed model of our project. This is the plan and section you can see here. I'm going to show it more in detail. And this is how the panels and layers all come together. And on the left bottom here, you can see the bearing structure. We also created a gateway between the modules, which you can change the length of. And by using that gateway, or maybe just using the module as a single one, you can create various formations. You can use module alone, one module alone, to create a pioneer base. And after that, you can extend it with gateways between the modules by separating every module, or you don't have to separate every module if the program doesn't need that, and you have to create bigger volumes. Or you can use this gateway at some parts of the station and just place the modules together without any gaps at other parts of the station. That would be a mixed formation. Or you can use all these four together to create a more complex formation. You can see plans and sections of some settlement types here. And after all, we also, again, performed a wind tunnel test for our final geometry. This is the module, a single module here. And this is the settlement without any gateways between the modules. And this is the one that separates every module with a gateway. And you can see the building process here. And in conclusion, we used computational methods to find the best solutions and cross-check our results with simulations. And we believe that we created a timeless module that can adapt to any settlement plan and any floor plan, which will survive in Antarctica. These are our references. And I want to show some renderings. This is the Horseshoe Island Barış presented. Thank you for listening.
Thank you, Ekin, for the presentation. Let's move on to the third group, who, as I said, is going to tell the account of how the winter garden could be designed. And Nisa is presenting.
Okay. Hello, we are group 3. My group friends are Betül Ünlü, Şemsi Barış Terzi, Nisanur Özdemir, Selçuk Özcan, and I, Nisa Çelebi. We are making optimization of winter garden in Turkey's Antarctic base. Due to term setup, we had to reference a previous undergraduate project. This project was a DKS project because it offers space solution and social area where researchers can feel better psychologically. When we analyzed Ron Roberts' research on Antarctic expedition, we observed that researchers working in Antarctica had a decrease in their mood and job satisfaction and increase in their sense of loneliness over time. Therefore, our motivation was to create a place where researchers can feel more comfortable. Our problem definition, it has been proved that psychological and physiological health condition of researchers exposed to harsh environmental condition of Antarctic continent have been adversely affected. Accordingly, design problem covers shell design of a winter garden, which will be developed by considering external weather condition of Antarctica and using healing effect of parameters such as light, humidity, ventilation, temperature, and sound. Before research part, I would like to give information about our process chart. In motivation stage, main problem was identified and references project was selected. In first stage, factors affecting psychology were examined and researchers were made on its integration with winter garden. Second stage is shell optimization and material selection required to make this winter garden resistant to harsh environment condition, and various analyses and plant selection were made to determine most effective plant type. In next stage, decoded details, grasshopper codes, and Arduino circuits were created to support these investigations, and VRWorks was created to experience winter garden. We have created work breakdown structure that includes necessary steps for us to reach final products in process. In this way, we realized more planned and systematic work, and our Gantt charts that we share works we set on our roadmap. Then we created morphological matrix that you have seen to determine outline of project and how it will proceed. I think it's not here, no problem. If we wanted the researchers to feel better, we should have done a research about what features the space pursues. As a result of our research, we have seen that features such as color, form, sound, and light have effects on the perception of space. We also decide that there should be plants in this place, which we will design based on the biofluid thesis. As a result of all this research and analysis, we decide to design a winter garden. As a result of President's research, we started shell optimization. Is shelling current project enough? Can other forms be tried? As a result of such as questions, we made wide analysis on forms that emerged with space and biosphere research, and these analyses led us to conclude that hemisphere is the most efficient form. Previous studies predicted that there would be a maximum of 61 people on top. Radius of space was determined as 9 meters by calculating social distances. For these 61 persons, we continue to work on a full hemisphere by determining height as 9 meters due to factors such as ease of installation. First, in plan optimization phase, we tabulated advantages and disadvantages of soil, soilless, soil and water coexistence. As a result of this table, situations where soil and water were used together come to 4. Afterwards, we examined soil and water settlement alternatives in 3 headings: central, fragmented, and frame. We evaluated the plan alternatives with studies such as sun and shade fall time analysis, calculation of soil, water, and plant areas to total area, maximum height range analysis that plants can reach. In order to achieve the final result, we had to know which plants were grown here. For this reason, 11 plants were selected according to parameters of plants and root length, lifetime and endurance, moisture requirement, and sun exposure. When we consider all parameters, central plant types that are compatible with plant selection can provide depth of pond and root and have most efficient sun rates came forward. After deciding on forms of shell, we had to choose material. We also listed the materials used in space and pole studies. At this stage, we thought that 2 layers shell setup is appropriate because it is both effective in use and easier in terms of maintenance. We separated materials to be used in outer shell and as carrier and non-carrier. Non-carrier materials, while high light transmittance and high strength. Carrier materials shouldn't have added much plastic and had high strength. We evaluated stratification alternatives we created with materials selected as a result of material research according to criteria such as transparency, ease of installation, and security level. And as a result, third alternatives came to fore. High transparency and light transmittance in outer wall is an important factor. Therefore, composite facade layers consisting of transparent aluminum and high thermal insulation silica aerogel were created. Steel was chosen as carrier material. As a result of the second step, we are able to provide thermal insulation up to 40 degrees with a thickness of 18 centimeters on outer wall of hemisphere of 9 meters radius and height. On inner wall, we recommend using moving solar control elements, ventilation ducts, artificial lighting, and UV lighting for plants. We recommend with fixed and mobile modules for interior shell. Factors that determine location of fixed and dynamic modules are to make maximum use of daylight, provide visual interaction of user with environment, technological elements to analyze in fixed modules, provide security. Interior facade is divided into 5 zones. First region, it faces west, which is the dominant wind direction. Second region, it is region where sun is taken most efficiently as a result of solar analysis. Third, fourth, and fifth regions provide transition between first and second regions. These regions determine the panel type distribution in interior design. In first zone, modules are mobile at visual angle and at levels where sun is taken most efficiently, and remaining modules are fixed. In the second zone, all modules are mobile. In third, fourth, and fifth regions, it was designed to increase mobile modules from first to second region. Based on this setup, panel combinations were created that can be used in 3, 4, 5 regions. Alternatives with different opening and movement types were produced for moving panels. These alternatives differ under following headings: movement on Z-axis, opening types, material types, and shading rates. It was decided to work on first panel type due to lower shadow drop rate, no Z-axis movement, and ease of application and maintenance. Based on analysis and research, thanks to outer wall, free from harsh external condition, it provides air conditioning with shell designed in inner layer, with dynamic shell elements, ventilation, lighting, and UV fixtures. It has pond, soil, and walking area in floor. It has clean room that allow users to be purified when entering and exiting. System section and detailed drawing of winter garden were produced. There are shell and panel system details. Here there is layer on floor, folding stage and joining details in panels, and all elements on shell. According to the Antarctic Treaty Environmental Protection Protocol, it is forbidden to bring microorganisms from outside. For this reason, there are clean rooms to purify before entering and after winter garden, so connection with other rooms was provided with clean room. We worked on consistency of winter garden with suggestion of other groups, module combination with group 1, and settlement alternatives with Group 4 were created. Flow chart was created for automation of system, which enables moving modules in winter garden to be opened, closed, heated, ventilated, and illuminated. This scheme guides us in transfer of data to digital media. This scheme was created for physical production process of study. Data in physical world were received with sensors. Then an Arduino and grasshopper connection was provided. Therefore, with codes created, information expected from sensor could be transferred to model. In Arduino studies, we can see reaction of the mobile and fixed modules in a part of shell according to ambient conditions. Yes. Different scenarios. Okay, we can skip. In created grosser code, we can observe behavior of facades according to ambient condition in scenarios where data of environment is simulated. In simulation, to control operation of ventilation and heating system, interior temperature, carbon dioxide and humidity value to provide control of panels and lighting. Circadian rhythms is day or night. If simulation is true, it's day. Outdoor and interior brightness level, whether there is a person inside, whether plants need light. After evaluating all this, we can see behavior of shell. Simulation contains 3 scenarios. In each scenario, some parameters are fixed and some are variable. You can distinguish change parameters with sign beside them. Okay. Now there are some images from Winter Garden. Yes. In indoor and outdoor view, we have center pond and frame soil area, and then walking area. Finally, we have prepared a module that can be experienced as VR works with summer and winter scenarios. You can access video with this QR code. Thank you for listening. Thank you.
Thank you, Lisa. And now we're going to go to the last group and go inside. And Cem, Güneş, and Pelin Arman are going to present together. They are going to be called the group Space Organization, I believe. Or they have a different name for themselves, I think. But
I'm sharing my screen, if it's okay.
Hello, my name is Pelin. On behalf of my group, me and Cem, we are going to present our 3-dimensional space organization algorithm for Antarctica mobile living module. The presentation consists of 3 chapters: pre-design studies, database and rule generation, and code applications. We created the morphological matrix to decide how to proceed. We've advanced our project through the options. We rated the matrix with the highest score. We have determined our decision topics. Then we made a work breakdown structure to complete our work systematically. Then we made a schedule divided into weeks and showing each member's work separately. As Group 2, we focus on designing mobile living modules that is a part of a central core. We design an algorithm that systematically generates plans for the living module according to the number of zones, object dimensions, and their relationships. Before we started building our database, we examined the interior designs of the boats, ISS, and Antarctic Research Centers. Then, our module consists of 3 layers. These are the main layer, the technical layer, and the storage layer, as you see in the diagram. We focused on the main layer where all the social activities occur. The algorithm is formed in 3 steps: zone generation, object placement, and evaluation. In the next slide, in this flow chart, we can determine the number of zones in the beginning of the algorithm. As all zones can work together, we can also form an alternative with 2, 3, and 4 zones. Now the generic objects. In the main layer, there are 5 zones: entrance, kitchen, common area, wet area, and personal space. We calculated the required minimum volume and area for each zone, then scored the relation to each other. Then we decided the generic objects to be used. We made the diagrammatic models of objects and brought them together to see the relationship with each other. All zones have a reference object which is placed first in the zone. The rest of the objects are placed consecutively after the reference. We constituted object placement algorithms for each zone individually. In the entrance, the reference object is connection point. For personal space, it's bed. For wet area, it's dressing cabin. For kitchen, it is sink. And for common area, it is the multi-purpose table. Then all zones brought together and different module alternatives were constituted. In the second stage, we started to work on the objects for improving their compactness, flexibility, and the multifunction. We decided to reduce the zone number from 5 to 3, as it is the most proper option for our design. Then we continue to determine the object placement rules on this scheme. We revised the dimensions and required circulation area for each object to be parametric. We do it for entrance, then in the next slide, the same thing for wet area. And for the living space. Living space is the combination of common area, personal space, and the kitchen. We set the reference object of living space as a kitchen unit, which contains all the objects of the kitchen area and a table or a sitting unit. We selected 3 different kitchen unit types according to their flexibility, expansion tolerance, and the space they covered. In the next slide, we are seeing the diagrammatic sections. These show us various design options in which the kitchen unit type and the bed are together compactly. Beds can be lifted and fixed to the wall. Thus, they can be used as a table or sitting unit when it is necessary. Then, we continued our studies with plans to see the relation between wet area and living space. They were so instructive to set up the rules of object placement and to constitute the evaluation criteria. Then, we set up the rules for placement of compact objects. And we show them with flowcharts. In the next slides, we see the flowcharts. For the living space, it is the most complicated zone among the others. So we decided to set up the rules for the kitchen units separately. We obtained 4 different kitchen unit types. Then for the living space, the algorithm chooses one of these kitchen units and randomly, and they set a reference object and continues to place the other objects consecutively. Now it's waste management. One of the most critical design problems in Antarctica is the waste management, which must be planned attentively to minimize the impacts of waste on Antarctica's environment. So we place required objects in storage layer. In the next slide, we will see in this diagram. And the next slide, we showed the rules in the flowchart. The space organization algorithm provides countless options. So we need an evaluation criteria to obtain the successful results. According to this, while ideal scenarios get 10 points, which is the highest score, the points decrease as combinations change. We consider compactness, functionality, comfort, and technical solutions while determining the evaluation conditions. And then finally, we generated manually 5 different modules with 3 zones, considering all algorithm rules, and we scored them. These are not the best solutions, but they're all generated by the algorithm.
Hello, I'm Cem Güneş, and I'm going to talk about the code application part of our project. And I want to start with this simplified flowchart. In our code, firstly, we try to create our zones. If it's successful, we continue to placing our objects. Then if the object placement is completed, the program ends. But if one of the steps is failed, we need to go to the beginning and start from the zone layout part. And to do that, we mainly use two platforms. First, we use processing. Then secondly, we use Rhino Grasshopper. In processing, we had opportunity to actually solve our two-dimensional problems. And I want to mention some of the important functions that we are using. We are starting with randomly choosing one of the cells for each zone and assigning them as the first cell of the zones. And after we randomly choosing one of the cells, then we check it's one of the four cells randomly. If the conditions are okay, and if the cell is empty, the zones starts to grow in chosen direction. Here we can see some simulations, animations of them. We can choose randomly cells and start growing. Then we check if the created zone is valid by controlling the area limits and the empty cell numbers. If generated zone is acceptable, we pass to object placement step. As each step has its own reference object, we are starting with placing them. Then we continue with other object placement consecutively in each zone. Then again, we are seeing the object as they have different colors. When we have valid zone, we are starting the object placement process. By placing the objects, we can choose placement distance, and we can also say if the object must be next to wall or not. In addition to these methods, we are using also rotation in order to trying another options to place our objects. We used Grasshopper as our second platform because it is more suitable for defining zones, space, and objects in 3 dimensions, and it's clearer to the relationship between objects and the zones. To start our code, the user must give some inputs for input. For example, width, height, length, cell size, and level might be some of them. And the algorithm creates empty space by using these information. After the creation of the empty space, the initial cells randomly, we place initial zones cells randomly as it was in processing. Then zone starts to grow by checking few conditions. First, we check one direction randomly. If it's empty, we can continue. Then we check the distance between the possible new cell and the initial cell. If the new cell is in limits, we can check the next condition. Lastly, we are checking we are controlling the maximum floor areas, and if the zone haven't exceeded the limit, the zone can grow. Then, after getting valid zone solution, we are filtering these zone borders in order to be able to fit our objects easily. We are basically checking each cell's surroundings and fix if there's something extraordinary. For example, we are seeing that one of the cells stuck between the other zones. In that case, the zone turns into surrounding zone. Then we pass to object placement. As it's already stated, we need to place with the reference objects. A reference object of the entrance in that example is exterior door. The reference object of the living space is kitchen unit, and the reference object of the wet area is toilet. Here, I want to mention that we are simplifying our furnitures. We are representing them as boxes. The objects boundaries represented as solid boxes, and the circulation area, the area that is needed to be used, represented as transparent boxes. And we are using base points to place our objects. Also, we defined our objects as vectors. Thanks to that, we can control their directions, mirror conditions, and rotations. here we can see the object placement order, and each object is linked to their previous objects. To place the object, first we are getting one of the possible directions. We find the closest cell in given direction and placing the base point to its corner. And when we try to fit the object to selected base point, we check if the placed cells are in the same zone and the zones are empty. If it's not, we continue to slide over the base points in given direction. Then if necessary, we try each possible rotations and mirrors. And by doing that, we are trying and eliminating all of the possible solutions. And if none of the options are valid, we need to go back to beginning and start from this zone generation. And here we are seeing in this slide, we see the solutions over plan view. When we take the example of the entrance zone, we can say that the door is placed as its default settings. Then changeover zone placed on the right-hand side with its default settings. After that, we placed closet by rotating it and no mirror. Then we placed interior door in front of the closet by mirroring it and rotating it. And we can follow each rotation and each transformation in given zones. And also we see boundaries and the base points of the each zones, and in each iteration, each run, our code generates unique solutions. And we can say that our algorithm still can be improved. We still don't have any evaluation parts, and we don't represent our walls. And the condition with units, kitchen units, for example, has some complicated code within itself, so they can be simplified. And we might have more basic empty or full conditions, and we can check collisions more easily. Thank you for listening. We had a QR code for AR experience, but I don't think we have that time for that. So it was our presentation. Thank you.
Jem, if you can leave it on for a few seconds when I talk over it, maybe people would like to, participants would like to try it out. The AR app, yes. Why don't you explain the QR codes?
Yeah, right-hand side, you should read the code and you should download the application to your Android mobile phone. Then you can scan the QR code in the middle. Then you can see our options by your phone.
Okay. Thank you to this last group for their comprehensive presentation. And also thank you, Efaytan, Nurcan Sütçü, and Ozan Balcı, that Pelin forgot to mention, but that was the whole group. We saw throughout the presentations not only design proposals for selected aspects of a complex architectural problem, but also a series of methods, either adapted applications of well-known techniques or original computational approaches that the studio researchers, the upcoming researchers that we just heard, developed. We also saw in all presentations the decision-making process that leads up to not ideal but satisfying solutions. So our aspiration for this outcome is that the knowledge produced here is of benefit and is translatable to other instances and parts of the design problem at hand or other design problems of kin. Yuksel?
Thank you very much. I've been listening to these presentations since the beginning of the semester with great pleasure, seriously. And now in its most completed form, I would like to thank to all the teams who did manage to come with wonderful work at the end of the process and somehow helped us prove the hypothesis that, I mean, involving actually scientific approaches might significantly increase the outcome of the design process. Thank you very much, first of all. And actually, I mean, we were a little bit, let's say, slower than we planned. I'd like to give the floor immediately to first to our young colleagues, Burak, Koray, Müge, and Inanç, if they have anything to add to this process, they have a significant contribution to this. Is there anything you would like to say? Müge, maybe first you. You need to open your microphone, Müge.
We can't hear you.
We can't hear Müge. Senak, could you open her microphone, maybe? Now, Müge,
is it okay now?
It's okay. Now it's okay.
No, it's okay.
First of all, thank you very much. You invite us as a guest your studio to see your works and make us to help our studio members as well. And it was really helpful for and nutritious for us also as a studio assistant. And also, I think this is so important doing that kind of research because, you know, Antarctica is quite important analog mission environment for space and further research as well. And that's why even for our research station, Turkish Research Station, assessments are important. But in the global thinking, if we see the further steps, it's so important to do that kind of research and studies. That's why I think, thank you so much.
Thank you. Yeah. Koray, you want to say something?
Yeah, I would also like to thank to you, Yuksel, and Mine to get us into your studio and let us mentor your students as much as we can. It was quite joyful at the studio when we were at the school, but with the remote interaction was also quite beneficial, and I think it was quite efficient in our senses. And yeah, for this subject, I would like to also thank you. The Antarctica matter was not in our scope till you brought it up, and it was great. Thank you. I hope we were useful in the group for the students and you as well.
Yeah. Thank you very much.
Thank you.
Burak, Inanç?
I would say, can you hear me?
Yes.
Yeah. I would say to thank you to everyone. It was an honor to me and great chance. Thank you. That's great.
Thank you, Burak. Inanç, would you like to say something?
Yes, I would like to say. First of all, I'm sorry about my camera. It's not working.
No problem.
The studio was very inspirational because they worked without non-stop, and they worked very hard. And also, even during this pandemic times, they managed to work together. I think it was very hard thing to do, but they managed it perfectly. That's what I was going to say.
Thank you, Inanç. Our young friends, colleagues actually mentored each one group, and actually their guidance, I believe, helped our students a lot. Thank you very much. Maybe we can give the floor to the questions, if we have any questions in the Q&A section, because you're able to ask through, in this webinar format, using the Q&A. Anybody from the audience would like to comment or ask a question to our students, to us, you're more than welcome. Nina, would you like to say something about this?
I don't see any questions, do you?
I don't see. I invited. Maybe there will be some. I don't know. In one way, I know it was a little bit tiring because it was a very dense presentation, trying to fit in a one semester very dense work and very technical work into a very compact document that has to be presented in 10, 15 minutes. So a little bit tiring. But I have to say this. There's an anecdote about Aziz Nesin. He writes 5 times everything in 5 different, let's say, techniques or even alphabets. And one of his fans asks him why. Isn't it difficult to do so? He says, I write it difficult so you can read it easy. So we need to work hard so you can live easy in those and safe in those environments. So that is the main thing, actually. It shows that as well. There is one question, by the way, anonymous attendee. It can be comment to everyone. Your projects are very good. You all focused on the design problem from different points. However, also, have you ever thought of presenting all of them as a whole project by superpose? They seem very disconnected. I can suggest this for the next level. Thank you very much. Very, very nice comment and question. Actually, we considered this. But this would be another layer of complication, since such an iterative process of working all the groups together and expecting input from each other in 3 hours per 1 week and 1 semester, 14 weeks study wouldn't be possible to do. So we strategically chose not to do so, but we somehow try to have a soft coordination, so everyone has a different aspect of the design, but kind of watching, observing what the others are doing and trying to be related as much as they can, but not to have a kind of complete integrated design. That requires a more professional and let's say well-connected environment, professional environment, that full-time dedication is required, I guess. I don't know if you would like to say anything about this, Mina, because this is to us, this question.
No, I would repeat what you said. Also, I mean, this is a question that we asked ourselves all the time throughout the semester, and also when we were devising this studio course as a research group. But I mean, of course, it's not an ideal research group because these researchers had other things to do, and this was just an engagement for a couple of hours, well, more than a couple of hours, because they worked a lot, obviously, and they really gave a lot. But it wasn't an ideal research group. If this was a lab with 20 people who worked on this alone, which would be ideal, right, Yuksel? That would be great.
We hope we can do that.
Then I think we can think about bringing together these different aspects. That would also require us being more involved as well. But a very good point that we also consistently ask ourselves. Now there are other comments, by the way.
Zehra Aktay, as a layman, I enjoyed listening to each and every group with pleasure. Thank you. Zehra is more of an artist than a layman. I know what she does and what she can do, and it's a great honor to hear this comment from her. Cengiz Tekin, thanks for the good webinar. Thank you for listening to us, Cengiz. Do we have other things? Maybe while we wait for a few more maybe questions or comments, I'd like to mention a few more names and thank them. One of them is Barbara Imhoff. Thanks to Müge that she introduced us to her and to Hoca. And so we could reach her, and she gave a wonderful lecture, inspiring lecture to us. She was maybe going to be with us, but she couldn't because of a tight schedule. And our jury members that join our, let's say, sessions during the time, the members of computation, architectural computation design program. And I don't know if there are other things to add, Mina.
No. We had good commentary from our jurors throughout the semester. We're always welcoming feedback.
Exactly. And also, of course, there are some. There is one, Alperen Acar. Thanks for the webinar and thanks for sharing this work with us. Thank you, Alperen, for watching us. What Mina said is actually very important, to have a kind of consistent work environment. Let's say a continuous team, continuous lab and resources to be able to come up with the best solution for this national and also international global mission that is ongoing in Antarctica. I mean, we all are hearing some news which are not that nice about this very fast, let's say, environmental change, not in good way, unfortunately. And the faster we are, the faster the scientists can contribute to solve or to understand the situation first. So we hope, I mean, through this webinar, we can be heard and like a flag race, the continuation of this study could be somehow organized. And for this, let's say, mediation, I also would like to thank again to the Circle for giving us the floor and enabling us to reach our audience. Anybody would like to say something from our group?
And we also have some of our group members in the attendees, if they want to
Yes.
share their thoughts with us, please type in.
Please. Looks like that is all. Then thank you very much for listening.
Thank you very much. This is from Circle again. Yeah, see you in the next seminar, hopefully.
Hopefully.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.